afternoon, or I suppose pre-afternoon, everyone. My name is Josh. I'm part of the Morrison Planetarium team at the California Academy of Sciences, and I am honored, nay, privileged to be here today with Dr. Eileen Gonzales for our Cosmic Conversations. Eileen, how are things over on the East Coast?
Things are going good. It's nice up here in Ithaca.
That's wonderful. We see the subway sign behind you.
We have the BDNYC group logo behind me. That was my former research group.
Oh, Brown Dwarfs, New York?
Yep.
City? Okay, very cool. So we're talking today about brown dwarfs, which is kind of a cool thing. I mean that as a joke. They are a very interesting classification of objects. They are cool, but they are also relatively low temperature. Eileen, what can you tell us about brown dwarfs?
So brown dwarfs are objects that fall in between stars and planets. They're not as massive as stars, so they don't sustain their own stable hydrogen burning in their cores, but they're more massive than planets. When you think of a brown dwarf, you can think of an object that's about the same size as Jupiter, but it's going to be anywhere between 15 to about 75 times as massive, and its temperature is going to range from a really cold day on Antarctica to about the center of a kiln.
And still, these are things we associate with stars, even though those are some very low temperatures for a star.
Yes.
Wow. Okay. So when we're talking about something that's the same size as Jupiter, but more massive, that would be something like if I've got a basketball compared to a bowling ball, they're about the same size, but one of them weighs a whole lot more?
Yes. Yeah, you can think of it just like that.
Okay. So a lot more stuff crammed into a similar amount of space. We're going to be showing you some really cool space visuals, including our brown dwarf friends. Using our UniView software, you can check that out just to the side of us. We can see a bunch of markers. These brownish markers are showing us the presence of brown dwarfs, but these are all relatively far away, at least compared to a human scale. Eileen, if we wanted to learn about something in our solar system that could teach us a little bit about brown dwarfs, would we look to our sun or somewhere else?
You wouldn't really look to the sun. You instead would want to look to Jupiter, since these things are more similar in size and they share a little bit more in similarities than brown dwarfs do to the sun.
Okay, so we're going to head out to Jupiter. This is going to be a relatively long trip. If we were making it aboard a spaceship, probably several years. Thankfully, we don't have to wait that long in our program. We are just flying straight out to see that wonderful stripy surface with actually, I think, the shadow of one of its moons falling on it, giving Jupiter a nice little freckle right there. So if we wanted to understand brown dwarfs a little better, what can Jupiter teach us?
So within the atmosphere of Jupiter, deep down in its gas layers, it actually has all of the different kinds of gases that we see in brown dwarfs. So if you start peeling away the top outer layers, you move to a cool brown dwarf that's called a T-dwarf. These things have their gases mainly methane, they have clouds. You keep peeling away more, you move to hotter brown dwarfs that we call L-dwarfs. These things are less cloudy. They're kind of in the middle. And you peel away even more, and then you can move to an M-dwarf, where for brown dwarfs, the later type objects are brown dwarfs, while the earlier type M-dwarfs are going to be what we know as stars.
Now, we're using a couple letters there, like L and M. Those are part of a classification system of stars as a whole, right? If I remember back to undergrad, there were a bunch of fun mnemonic devices to remember the classifications of stars.
Yes. So for the classification of stars, you typically go down to M dwarfs. And then after that, brown dwarfs don't actually fall on what we call the main sequence. These things, because they start off as hot as they're going to be, and over time they continuously cool, they never reach a main sequence like a star because they're not having that stable hydrogen burning. So for brown dwarfs, we have them spectral typed as M, L, T, and Y. And for the M dwarfs, the objects that are brown dwarfs are going to be the ones that are younger. And you can go down to about midway through the L sequence where you still have some stars, where you're sharing that boundary of stars and brown dwarfs. By the time you get to T and Y dwarfs, you're into brown dwarfs and then things that could be free-floating giant planets.
So the thing that would separate our sun from a brown dwarf would be the fact that our sun is made of similar ingredients, hydrogen and helium, but it's using up those ingredients to make more energy.
Right. But then another difference is that because these objects are very cool, for the sun, you're seeing your abundance of hydrogen and helium. with these objects, because they're so cool, we are seeing molecules in their atmosphere. So we're seeing things like carbon dioxide and methane. And as we move to cooler objects, you start to see cloud formations. So you might have an iron cloud or a corundum cloud. And we don't see these things on the surface of the sun because it's just so much hotter than these objects are.
And then our thing that would separate them from a Jupiter type object is the amount of that same material. But also Jupiter is hotter on its surface than cooler on the surface than some of these objects.
Yes. So Jupiter is, you can think of Jupiter more towards the lower end as you move through the cooler and cooler brown dwarfs. Brown dwarfs go down to about 250 Kelvin. You might not use Kelvin very typically, but you can think of the coolest brown dwarf to the temperature of Jupiter of being about 100 degrees difference between the two.
In astronomical terms, that really doesn't seem like that much.
Yeah.
Okay, so we're looking at a whole bunch of brown dwarfs spread out across the sky, but I want to switch over to something else you mentioned before, which were M dwarfs. So can you tell us a little bit about these M dwarfs?
So M dwarfs are the most abundant kind of star in our galaxy. These are low mass stars. They're less massive than the sun. And a lot of them are super interesting right now because people are looking for planets around other stars. And we're really driving towards looking for small terrestrial sized planets. And if you use a method called the transit method, where you're looking for the change in brightness that we observe from the light of that star as a planet crosses in front of it. If you want to find a small planet, it's best to look around small stars so you'll have a bigger change in that brightness. So there's the Kepler Space Telescope that was looking at one piece of the sky, and it's moved on to K2, and most recently, observations by TESS, where you're finding lots of planets around these small stars.
Now, I just want to call folks' attention to this. Maximize it. Do whatever you can to see as much detail on this window as possible. I want to show you something really cool. Eileen mentioned how common these stars were. This is a very crowded star field. This is what our eyes would be seeing at a similar distance. The stars we go outside and see in the night sky are much less abundant. We're not that far away from our own sun. When we add in those M dwarfs, you can see just how crowded the sky gets. We wouldn't really be able to see these things from Earth with just our eyes, right?
Right. So a majority of the light from these objects is coming from the infrared. So that's going to be the heat that comes off of our body. So it's not like when we're looking at the sun and we see that invisible light. These are much cooler objects. So we need to use special instruments to see them.
So backing up, again, you get to see just how incredibly dense that field is. I'm going to toggle it one last time. I just think this is the coolest thing ever. Pun not intended that time. But we can show you a different distribution of those brown dwarfs. And now you can see just how abundant they are too. Are there probably as many brown dwarfs out there as there are M dwarfs?
There's probably just as many, if not more. But currently, the brown dwarfs we know about are ones that are nearby to our solar neighborhood. Because these are even fainter than M dwarfs, it gets pretty difficult to find things that are a whole lot further away. So we're looking for things that are relatively nearby.
Now, interestingly enough, you can see kind of a change in the distribution of these in specific directions. Like if I look over here, all of a sudden, the brown dwarf population in this part of the sky gets very, very low. And if I zoom in, we can see kind of why that is. So can you explain why we see more brown dwarfs in some directions than others?
Yeah, so when we look for brown dwarfs, and basically for a majority of stars in general, it's typically much easier to find them away from the plane of the Milky Way. The plane of the Milky Way is where we're going to have lots of gas and dust, and that's going to obscure our view. So a lot of the objects that we look for, they're much easier to find in regions that are away from it because we don't have that gas and dust. And particularly when we're using the infrared, that's going to make it a little bit more difficult to find these objects. So I think we're looking, do we have the Milky Way up right now?
Currently invisible, but if you folks want to see just how challenging it would be, if you want to see the Milky Way in infrared, the Milky Way is actually quite bright in infrared.
Yes. So we can see through the gas and dust that's in the optical. We're seeing bright regions, particularly also regions where we're seeing star formation. So baby stars are being born, but it's also very hard to look for brown dwarfs within this because these are also very faint. But recently with Gaia DR2, we did find a new brown dwarf classified as an L-type object that was pretty near to us, that was found in the plane of the Milky Way, and it was found because of how it's moving. So because it's close to us, it's a fast-moving object. And using how it moves through various data sets, we could determine this new object, even though it's in such a crowded and dense region.
So just to give folks that angular perspective, you can see, I don't know, a couple dozen brown dwarfs in our view at the moment. But if we tilt our view, you get to see just how common they are away from the plane of our galaxy, where we're not getting as much interference. That's just a really amazing view. And you said most of these objects we're finding are relatively nearby, not that far from our own solar system.
Yes.
So astronomers are often pretty horrible at using the term nearby or far away in completely inapplicable context. Can you explain what nearby would mean around here?
So nearby in this context is, so we use a term called parsecs. So within like 100 parsecs. So a parsec is a parallax arc second, and you're probably more common with terms like light years. So the conversion is about 3 light years to 1 parsec. So these are relatively nearby on the span of the size of the Milky Way, where you're looking at it being 8 kiloparsecs across. So these are much closer to us than, say, looking at the opposite side of the galaxy.
So we did a comparison in the planetarium once upon a time where we said if the solar system were 2 inches across, the Milky Way would be about the size of North America. So these would be things within maybe your town, not across the continent from us. Okay. Medium distance. That's wonderful. Okay, so we can see their distribution here, but not just content to see markers. There's a couple interesting brown dwarfs that are maybe not the ones you personally have been researching, but ones that are in some way similar. Can you tell us about, I'm going to mess up the name, WO855?
Yes, WISE 0855. It is my thesis advisor's favorite object. WISE 0855 is the coolest brown dwarf. It is only about 100 Kelvin hotter than Jupiter. It's got water ice clouds, and it was a really unique object to find. It was missed in a lot of other surveys because it's so faint, and getting its spectrum, so what it's made up of. Have you talked about spectrum on this before?
We've talked a little bit about it, but a refresher is always welcome.
Yes. So the spectrum of the object is its chemical makeup. So to observe this object, because it's so faint, I believe it took about 14 hours to get its spectrum. And what's really cool is it came out that we could detect water ice clouds in it.
Okay, so that's a water ice cloud, perhaps similar to the clouds we would see here on Earth, floating around this star-like object?
Yes.
Wow.
And this object it's interesting because it's really on the border between planets and brown dwarfs, less on the border between a star and a planet. Its mass is about 3 to 10 Jupiter masses. And I had said earlier, the mass limit for brown dwarfs is about 15 to 13. And we kind of draw this arbitrary line where you can
Humans
stop.
love those.
Yes. Humans love to classify things with arbitrary bins. And that line is drawn where you can no longer fuse deuterium. So this thing really is right at the edge, and it could be a planet. And if it's a planet, it's like a free floating planet. So, there's questions of, did it form by itself? Did it get ejected from some system? So it's super interesting to use to try to understand, planet formation, brown dwarf formation, these things that we still have questions about.
Now, a couple things pop up in my mind. Is an object like this thought to be a very old object, a very young object, or we're not sure of the age?
So it really depends. For brown dwarfs, any brown dwarf that has ever been formed is still alive and still around. This is not something you see for much higher massive stars, because those things, they run out of their fuel much faster. They burn through it. But because brown dwarfs aren't doing that and they're just cooling over time, every brown dwarf that we've observed is still here. So it's really hard to determine ages of these objects unless you can place them in things that are known as nearby young moving groups, where you can use higher mass stars to determine their ages. I believe 0855 is just in the field. So it's got a wide span for its age. So it's probably a little bit older because it's not in those moving groups, but we can't pinpoint an exact age on it.
Fair enough. Could it be a star that died slowly as opposed to the cataclysmic deaths? Is a question from Israel.
It's probably not a star that died slowly. If that was to happen, it would probably be a much hotter object for the span of the age of the universe. So you could think of maybe a hotter brown dwarf that has cooled over time, but this is likely to be an object that formed at a fairly cool temperature and has been continuously cooling down, but not forming at something that's, closer to the temperature of an M dwarf.
Now, quick question. You mentioned something earlier that I know we're not going to find on the periodic table, no matter how long we look at it. Deuterium. What is a deuterium?
So deuterium is heavy hydrogen?
We've called it heavy hydrogen a lot.
Yeah.
That's kind of a goofy name for it.
It is...
We've had a guest describe it to us as when a hydrogen spends a little bit too long hanging around protons, you get an extra proton hanging off, or excuse me, an extra neutron. So hydrogen with an atomic weight of 2 as opposed to 1 while still being hydrogen. Now, another object you mentioned was LSR, I'm going to mess this one up too, J1835.
Yes, 1835 plus 3259. So this is an interesting object. It was actually going to be part of my thesis sample. I did not get to complete what I was planning for it. So my thesis, a large part, is on understanding the atmospheres of some of these objects and doing them through something we call atmospheric retrievals. So it's a very complicated word, but really what we're doing is we're starting from the data we observe. So when we get the spectrum of the object, we're trying to figure out what gases it's made up of and how much of that it is. This object is really interesting because it's one of the brown dwarfs that have been observed in the radio. And this is a variable object. It varies in the optical, the infrared, and the radio. And typically in brown dwarf science, when we think about variability, we typically think of that being tied to clouds on the surface. So we're seeing down at different depths for different patchiness. But for this object, it actually has aurora. And we're thinking that that is due to its magnetic activity. So that's the signature we're seeing in its variability. So I think we have switched the aurora on.
You can see some of them on the poles.
Yeah.
Now, I've definitely seen photos similar to this, Hubble shots of Jupiter and Saturn, I believe, showing off auroral displays. Is that a related phenomenon, or is this doing something different that just looks similar?
It's probably a related phenomenon. I think that we still haven't figured out exactly what's causing aurora on brown dwarfs, but it should be something that's pretty common on a fair number of them. And it's probably driven by its magnetic activity.
Looks like it would be absolutely beautiful to see, but I can imagine it being not at all comfortable to hang out on the surface of a brown dwarf, if possible.
No. It probably wouldn't be comfortable to hang out on the surface. When you think about what's in the atmosphere of brown dwarfs, one thing that comes to mind for some of the hotter ones is iron. And when you think of what iron would be like in a liquid form or in a cloud, I've had someone describe to me as thinking of tiny iron BBs raining down on you. So that
Not a good
probably
time.
wouldn't be a good environment
No.
to live in. Definitely pretty cool to
Absolutely
think about, but I don't think I'd want that raining down on me.
Sounds like the heavy metal planet.
Yes.
Now, there's a little bit of a color change between this and the brown dwarf we just saw. Our artists in our engineering studio work very hard to replicate accurate science in all the images we show. Why would one of these appear so different than another?
Primarily what we're looking at is the difference in temperature of the two objects. So WISE 0855 is a Y-class brown dwarf. That's going to be one of the coolest types of brown dwarfs. In 1835, this is an M dwarf. So it's a hotter object. So we're just seeing more of its light coming out in the infrared. So it's going to be that brighter red color. Whereas the WISE 0855, while most of its light is coming on the infrared, it's coming out in longer wavelengths. So it's going to be looking dimmer to our eyes.
Fair enough.
Our color-coded eyes, if you will.
Now, we also had one more object, J111-1137. This one, I believe, is a two-parter, isn't it?
Yes. So this is a binary system. It's a really interesting one because it's extremely red, an extremely young system. These objects are very close to one another. They're separated by a very small amount. And I actually wanted to use this system kind of as an analog to talk about a system I work on, which is essentially a complete opposite to this system. This one's very young. They're very nearby. The work I've done is on another brown dwarf binary system, but they're on the complete opposite end. They're two very old objects that are actually widely separated. So for this system, we haven't been able to individually resolve both objects. We can tell it's a binary through its spectrum, but for the one I've worked on called SCSS J1416AB, we've resolved them individually by themselves. They're separated at about twice the distance that Pluto is to the sun. And these guys are two very old objects. They're something we call subdwarfs. And a subdwarf is really just an object that has a metallicity that's lower than that of the sun. So it was probably formed much earlier. And it could be in the galactic halo, or in this case, these objects are within the disk, but something we call the thick disk. So it's puffed up a little bit. It's gone around the galaxy a couple of times. These guys are really interesting because one is an L dwarf and one is a T dwarf. And our question is, because these objects are so old, did they form and evolve together? Was one captured? And what can this binary tell us about formation and evolution of these objects? So I've been trying to look at the atmospheres of these two objects to try to probe more and figure out what we can. And interestingly, one of them is a very cloudy object, while the other is cloud-free.
Interesting kind of odd couple going on there.
Yeah.
Yin-yang.
Yes, very yin-yang.
Okay. Well, that is absolutely fantastic. I wanted to leave some time for questions. What drew you to the study of brown dwarfs, and what are you interested in finding as we get more technologies to explore these objects?
Well, what really drew me into studying brown dwarfs is that it's really a topic that's kind of brushed over in any intro astronomy class. Maybe it's dusted in and you talk about stars, you're like, oh, there are these things called brown dwarfs, but whatever, we're moving on. And I was always really curious. In undergrad, I wrote a paper on them as a project, and it's something I really wanted to know about more because these are these weird kind of objects that lie in between, and they're really helpful in understanding how things have formed in the universe. And what I'm probably most interested in learning about is clouds on these objects. What is the composition of clouds if they have them, and how can that teach us about giant extrasolar planets, and how can we improve techniques that we use on these giant planets to one day move towards using these techniques when we look for small Earth-like planets?
Okay, that sounds like I can verify in a lot of lesser, not quite graduate degree astronomy courses. They mention they exist, they mention they're common, and then you move on to the next thing because our universe is big and complicated and there's just so much to cover. But I think they are a great reminder of the fact that our universe is bigger and more complicated than our eyes reveal, and there is always more stuff out there for us to check out and to learn, and you never know what information you're going to extract from something that seems small and humble can teach you an awful lot. So, Eileen, if there's any further questions, is there a place folks might be able to contact you? I know you have some social media accounts you're active on.
Yes, I am on Twitter. My Twitter handle is egonzales788. Or that's probably the best place to reach me to send a message.
Fantastic. Well, thank you so much for tuning in and sharing your expertise. Any other communication you want to send out to our watchers?
I don't have any last things to say, but go look outside and check out what you can.
Fantastic. Thank you so much for spending some time with us and sharing your expertise. And Dr. Gonzalez has a really fun social media feed. Check it out. I've been enjoying it myself. On behalf of all of us at Morrison Planetarium, thank you, and thank you to our watchers. And we encourage all of you to, if you're not outside looking up at the stars, take good care of yourself, stay home, and have a wonderful rest